Hello friends, welcome back to all about structural analysis and design. So today in this video we will again see the analysis of continuous beam by Kani's method. But the difference between this video and my previous video is both the end supports were fixed in the previous video, whereas in this particular video one side is fixed and another side is roller support. Okay, so what modification has to be done in this particular video, we will see it. Otherwise the steps remains same. The first step will be to find out fixed end moments, then rotation factors, then Kani's representation and contribution, and then we have to calculate final moments. So only thing is the modification when the end supports are not fixed. I will show you how to do it in this particular problem. So the first step will be to find out fixed end moments. So in this particular problem there are two type of loads, the point load which is at the center and UDL. For point load at the center the fixed end moments is WL by 8. So MFAB will be anti-clockwise, therefore negative. MFBA will be clockwise, therefore positive. So MFAB is equals to minus WL by 8. So here W is 50, that is minus, into L is 4 divided by 8. So therefore this will become minus 25 kilonewton meter. Whereas MFBA will be WL by 8. So only this is positive because it is clockwise. So it will become 25 kilonewton meter. Next, MFBC. So again MFBC is anti-clockwise, negative. MFCB will be positive because it is clockwise, and it is UDL, and for UDL the formula is WL square by 12. So MFBC is equals to minus WL square by 12. So here W is 20, L is 4 meters, so this comes out to be minus 26.67 kilonewton meter, whereas MFCB will be positive WL square by 12. So it comes out to be 26.67 kilonewton meter with positive sign. Next, again point load at the center, MFCD will be anti-clockwise, that is negative. MFDC will be clockwise, that will be positive. So MFCD will be negative because it is anti-clockwise. So again WL by 8. So minus 54 divided by 8. So again it is minus 25, and this will be MFDC WL by 8 positive 25 kilonewton meter. So this step again remains same in slope deflection method, moment distribution method, and this Kani's method. So again I will be sharing the link in the description box of all of the playlist of both the methods, so kindly you can go through it. Now the important part in this particular video is we know that the moment at D is 0 because it is a roller support. The moment is there at A, correct? So this here moment ultimately we will be getting 0 by calculating the final moments. So already we know that here at D the moment is 0. So you can go with the conventional method. Okay, the previous method what we have seen, you can go with that one, but the only difference will be the iterations will be more. But with the modification which I will show you now in this video, the steps will become less. So let's see the modification method. So now I'll write here as the moment at D is 0. Therefore, modification can be done in last span. Last span means CD span here in this case. Okay, so we are not going to have anything modification here because it is fixed end. Okay, so now what we have to do is, if you want to make this DC as 0, okay, so now we have to change the value of MFCD. Already the MFCD is minus 25. So again new value will come for MFCD. So that we will denote it as M dash FCD is equals to MFCD, which we have calculated, minus 0.5 into unbalanced moment at D. Moment at D, which is nothing but MFDC. So I'll write down here the values so that it will be clear. So MFCD, which we had calculated, it will become minus 25. So this minus 0.5 means half into unbalanced moment, that is 25, that is MFDC. So new value of MFCD will become minus 37.5 kilonewton meter. So I think you have understood what we have done. We have made this DC as 0, and with respect to this DC as 0, the new value of MFCD will be coming into picture. So old MFCD value was minus 25. So that minus 25 minus 0.5 times of the old MFDC value, that is 25. So once you calculate this, you will get new value of MFCD, that is minus 37.5 kilonewton meter. So therefore now MFDC will be 0 kilonewton meter. So like this way you have to modify the last span. Now the next part is to find out the rotation factors. So as we have done the D as 0, the moment at D as 0, there will be only two joints. So there will be only two joints, B and C, and the members from B is BA, BC, members from C is CB and CD. Okay. So now here joints are two. So this will be B joint and this will be C joint, and the members are BA, BC and CB and CD. Okay, so these are the members. So now the stiffness. So for BA it is 4 EI by L. Correct. Once again I'll explain these things. I have explained in moment distribution method also, where the stiffness was changing. So now BA is 4 EI by L because the last end is fixed, so no change in the stiffness. BC also it will be 4 EI by L because after C there is one span. CB also 4 EI by L because after B there is a span, and CD. Okay. Now remember, when you go for the modification method, means if you calculate the new MFCD value, the stiffness will be 3 EI by L for CD. Okay, and not 4 EI by L. So there are three members of which are having stiffness 4 EI by L, and one member, that is CD, which is having stiffness 3 EI by L. So this will be 4 EI by L, BC will be 4 EI by L, CB also will be 4 EI by L, and CD will be 3 EI by L. So this is again small change you have to remember. Okay, so I value and E value is not given, so it is assumed as 1. So here BA, the span is 4, so 4 EI by 4, it will be EI. So this also will be EI, EI, and this will be 3 EI by 4, 0.75 EI. Now sigma K will be 2 EI, and this will be 1.75 EI. Now rotation factor, how to calculate? It is minus half K by sigma K. So K already we have, sigma K is also there, so multiply with minus 0.5. So rotation factor for BA will be minus 0.25, BC will be minus 0.25, CB will be minus 0.286, and CD will be minus 0.214. So here the important thing you have to remember is, first is if you go for modification, the last span stiffness will be 3 EI by L. Okay, then you have to remember how to calculate rotation factor, that is minus half into K by sigma K. Now once you have done with the rotation factors, now the Kani's representation you have to draw in the form of box. Okay, so this was fixed end, then this is B and C joints, and this is D joint. This is already we have made 0. Okay, so that's why there is no another box. So if you want to go with the traditional method without modification, one more box will come into this particular representation. Okay, so now what you have to do is you have to write down the fixed end moment values. So MF AB was minus 25, MF BA was positive 25, MF BC was minus 26.67. For clearance, I'll write down here, this is A, this is B, this is C, and this is D. So MFCB was positive 26.67. Now MFCD, the new value you have to write down, that is minus 37.5, and this will be 0 MFDC. Okay, so don't write old MFCD value here. Okay, the new value which we have done with modification, you have to write down. So once you have done this, then you have to write down the rotation factors which we just calculated now. So BA was minus 0.25. So in this you have to write down here. Then BC is minus 0.25. CB is minus 0.286. And CD is minus 0.214. So these value you have to write down. Next, what you have to write down is the summation of the moments. So 25 minus 26.67, it will become minus 1.67, and 26.67 minus 37.5, it will become minus 10.83. So this completes the input of Kani's representation. Once you have done this, now you need to calculate the contributions. The formula was rotation factor into summation of fixed end moments at the joints plus rotation contributions from far end. Okay, so now this is the first iteration. So the rotation factor is minus 0.25 into minus 1.67. The far end for this B is, one is C here, CB, and another is AB. So here there are no rotation contribution as far as first iteration is concerned. So the value will be minus 0.25 into minus 1.67 plus 0. So it comes out to be 0.4175. 0.4175. And also because of this rotation factor remains same here, the value is same, 0.4175. Okay, so those who are seeing this video for the first time, I'll write down the formula here. So the contribution you can calculate by taking rotation factor into summation of fixed end moment at joint plus rotation contributions from far end. Okay, so this will be your formula to calculate the contributions. So now similarly you have to calculate the contribution at C joint. So now what will happen, the rotation factor is minus 0.286 into summation of fixed end moment at joint. So this is summation minus 10.83 plus rotation contribution from far end. The far end is here D and one more is B. So far end contribution is plus 0.4175. So therefore minus 0.286 into minus 10.83 plus 0.475, you will get here 2.98 value. Similarly, minus 0.214 into minus 10.83 plus 0.4175. So you will get here 2.23. So this completes your first iteration values. Now the second iteration values, again RF, that is minus 0.25 into minus 1.67. Now rotation contribution from far end. So in previous first iteration the rotation contribution was 0. Now here the rotation contribution from C, it will come, that is plus 2.98. So minus 0.25 into minus 1.67 plus 2.98. So you will get minus 0.3275. Okay, so because rotation factor remains same, so here this value also will remain same. Now second iteration for C, minus 0.286 into minus 10.83 plus rotation contribution from far end, that is minus 0.3275. So the value will be 3.191. Then minus 0.214 into minus 10.83 minus 0.3275. The value will be 2.38. Okay, so whatever the sign is there at the far end, that you have to take it. Okay, so if it is minus minus, then if it is positive, at least positive, but the formula you have to follow this one. Next, the third iteration, minus 0.25 into minus 1.67 plus 3.191. So you'll get minus 0.380. So this again will remain same because the rotation factor is same. Next, minus 0.286 into minus 10.83 plus here it is minus in contribution, so minus 0.380. So their value will be 3.20. Minus 0.214 into minus 10.83 minus 0.380. So 2.39. So till when we have to continue this problem? Till where we get the similar values between two rows. Okay, so another iteration we need here. So minus 0.25 into minus 1.67 plus 3.20, you will get minus 0.382. So this again will remain same. Minus 0.286 into minus 10.83 minus 0.382, you will get 3.20. Minus 0.214 into minus 10.83 minus 0.382, 2.39. So if you see carefully here, these two values are almost same in all the contributions. So this will be your final contribution values. Okay, this we have to take and carry forward to the final moment calculations. So this will be your final moment calculation table. First you have to write down the joints, that is A, B, C, D. Next you have to write down fixed end moments. So AB was minus 25, BA was positive 25, BC minus 26.67, CB 26.67, CD the modified value, that is minus 37.5, and DC was 0. Now near end contributions. So near end contributions you have to remember always multiply by 2 times. So 2 into near end contribution. So near end contribution for AB. So near end is A. So contribution is 0. So 2 into 0. Now BA near end contribution is minus 0.382. So 2 into minus 0.382. Okay. Next, BC. BC the near end is this one. BC near end is minus 0.382. So 2 into minus 0.382. Next, CB near end is 3.20. So 2 into 3.20. Okay. So CD near end is 2.39. So 2 into 2.39. Don't write anything here. Okay, already it is 0. So if you make 0, there will be no values in this particular column. So this will be 0. So this will be minus 0.764. This will be minus 0.764. So here it is minus, consider it minus. So this will be 6.4. This will be 4.78. Okay, always remember near end contribution you have to multiply 2 times. Now far end contribution. So far end for AB is B, so that is minus 0.382. So write down here minus 0.382 far end. So B is far end. Now BA far end is A, so here the value will be 0. Next, BC the far end is C, that is 3.20. CB the far end is minus 0.382. CD D end is this one 0. And DC, don't write anything of far value for C1 because already D is 0, so we don't need any contribution here. Okay, so therefore don't write anything in this particular column. Now final moments. Final moment is nothing but all summation you have to do. Minus 25 plus 0 minus 0.382, you will get minus 25.382. 25 minus 0.764, so 24.236. So this will be minus 24.236. So 26.67 plus 6.4 minus 0.382, 32.68, and this will be minus 32 point around 7. Okay, and this will be 0. So our aim is satisfied. So this was having moment because it was fixed end. So B, so if you consider BA and BC, the summation is 0, CB and CD summation is 0, and D is already 0 because directly it was roller support. Okay, so these are the final moments. So once you get the final moments, then you have to draw the bending moment diagram. So this bending moment diagram with respect to the original loading condition I have drawn. So once you do this, then you have to overlap the final moment values. So AB was minus 25. So this will be your minus 25 value. Next, BA BC was 24.236. So somewhere near 25 only will mark here. Next, CB CD is 32.68. So you can mark it here, and this value was 0 here. So now we have to join these things to get the final bending moment diagram. So join here for 0 part. Okay, so this will be a net bending moment diagram. So this above this line it is negative, above this line it is positive. So this will be 0 and 0. Okay, so you can write the values also. So 25.382, this will be 24.236, this will be 32.68, and this will be 0. So this is how you have to analyze a continuous beam by Kani's method when the end support is not fixed one. Okay, so I have shown you how to modify the last span. You can either go with this method or traditional method. Traditional method, 3 boxes will come, and their stiffness, all members you have to take 4 EI by L. I hope you have understood this problem. If you like it, please share it with your friends, and don't forget to subscribe all about structural analysis and design, and also press the bell icon for the latest notifications of my videos in civil and structural engineering. Thank you, friends.